Welcome to our study of atmospheric moisture. Let's start with the hydrological cycle, commonly known as the water cycle. This is the continuous exchange of water between the atmosphere, the oceans, and the continents. Because the total amount of moisture in the entire Earth system remains constant, there has to be a balance. The water cycle maintains this equilibrium, ensuring that the amount of water lost through evapotranspiration equals the amount returned through precipitation. Now, let's zoom in on the water vapor itself, which we call humidity. Water vapor makes up anywhere from 0 to 4% of the atmosphere's volume, averaging around 2% globally. To measure this invisible gas, meteorologists use an instrument called a hygrometer. Why do we care so much about this tiny percentage of water vapor? First, it plays a massive role in the Earth's heat budget by absorbing both incoming solar radiation and outcoming terrestrial radiation. Second, it stores latent energy, which is the hidden fuel that powers massive weather systems like storms and cyclones. Atmospheric moisture also directly impacts our daily lives by affecting the sensible temperature, which is how hot or cold it actually feels to the human body. High humidity slows down the evaporation of sweat, which drastically reduces our body's natural cooling rate. Let's break down the different ways we measure humidity, starting with absolute humidity. This is the actual physical amount of water vapor present in a specific volume of air. It is calculated by taking the weight of the water vapor and dividing it by the volume of air, usually expressed in grams per cubic meter. Absolute humidity isn't the same everywhere. It is significantly higher over oceans because there is simply more water available to evaporate. Furthermore, the ability of air to hold this moisture depends entirely on its temperature. Warm air can hold a lot of moisture, whereas cold air is mostly dry because the water vapor condenses and falls out as snow or dew. The most common measurement you will hear in weather reports is relative humidity. Instead of an absolute weight, this is a percentage. It compares the actual amount of moisture in the air to the maximum amount of moisture that same air could possibly hold at its current temperature. When air holds exactly as much moisture as it can at a given temperature, we call it saturated, meaning its relative humidity is 100%. At this point, evaporation stops. But if the air only has half the moisture it can carry, the relative humidity is 50%, and evaporation can easily take place. This diagram perfectly illustrates how temperature changes capacity. Look at the 10-degree air on the left. It is completely full, so relative humidity is 100%. But if we warm that exact same air to 30 degrees, the capacity expands dramatically. Even though the actual amount of water vapor hasn't changed, the relative humidity drops to 28% because the air's capacity is now much larger. Geographically, relative humidity is highest over the oceans and lowest over the continents. This makes sense because, as we learned earlier, absolute humidity is greater over the oceans due to the vast availability of water for evaporation. So, how can relative humidity change? There are two main ways. The first is straightforward. Add more moisture to the air through evaporation. By increasing the absolute humidity while keeping the temperature the same, the relative humidity percentage goes up. This second way to change relative humidity is by changing the air temperature. If you cool the air down, its capacity to hold moisture shrinks. Therefore, without adding a single drop of new water, a decrease in temperature will cause the relative humidity to increase, bringing the air closer to its saturation point. Let's look at a mathematical example to make this concrete. Imagine 1 cubic meter of air at temperature T. Let's say its maximum capacity is 0.5 kilograms of water vapor, but it currently only holds 0.2 kilograms. Its absolute humidity is 0.2, and its relative humidity is 40%. To reach 100%, we could simply evaporate 0.3 kilograms more water into it. But what if we drop the temperature instead? Let's say cooling the air by 1 degree reduces its capacity by 0.1 kilograms. If we drop the temperature by 2 degrees, the maximum capacity shrinks from 0.5 to 0.3 kilograms. Since we already have 0.2 kilograms of moisture, we now only need to add 0.1 kilograms to reach full saturation. This brings us to a crucial concept, the dew point. The dew point is the exact temperature to which air must be cooled to reach 100% relative humidity. When the air temperature drops to the dew point, saturation occurs, and water vapor begins to condense into liquid, like dew on morning grass. There is a third way to measure humidity, called specific humidity. Unlike absolute humidity, which uses volume, specific humidity measures the weight of water vapor per unit weight of air, usually grams per kilograms. Because it relies entirely on mass, specific humidity does not change if the air expands or contracts due to temperature or pressure changes. It only changes if moisture is physically added or removed. Let's test our understanding with a past exam question. Assertion A states moisture is related to latitude. Reason R states moisture capacity is related to temperature. Since temperatures generally fall as we move from the equator to the poles, meaning higher latitudes, the capacity to hold moisture falls too. Therefore, both statements are true, and the temperature change perfectly explains the latitude change. The answer is A. Moving on from humidity, let's examine the process that creates it, evaporation. This is the transformation of liquid water into a gaseous state. Globally, the vast oceans contribute 84% of the annual total evaporation, while the continents contribute the remaining 16%. Where does the most evaporation happen? Over the oceans, the highest annual evaporation occurs in the subtropics, specifically the western North Atlantic and North Pacific, driven by warm ocean currents like the Gulf Stream and Kuroshio Current. On land, the maximum occurs at the equator, thanks to intense sunlight and dense transpiring vegetation. Several factors control the rate of evaporation. Naturally, you need a good amount of water and a large surface area. Higher temperatures also speed up the process. Importantly, relative humidity plays a huge role. Dry air with low relative humidity has plenty of empty space for new moisture, which significantly increases the evaporation rate. Wind is another major factor. As water evaporates, the layer of air right above the surface gets saturated. Wind blows this saturated air away and replaces it with dry air, keeping evaporation going strong. Additionally, lower atmospheric pressure over a liquid surface makes it easier for water molecules to escape, thereby increasing the evaporation rate. Finally, the composition of the water matters. Salt gets in the way of water molecules trying to escape, meaning evaporation is inversely proportional to salinity. In fact, fresh water evaporates about 5% faster than ocean water. Also, thanks to the active process of transpiration, water generally evaporates at a faster rate from plants than it does from bare soil. We will look at what happens after evaporation next. Moving right along to our next major atmospheric process, let us examine condensation. Condensation is simply the transformation of water vapor into liquid water. This process is driven by the loss of heat. When water changes from a gas to a liquid, it releases energy into the surrounding environment, which we call the latent heat of condensation. This is the exact opposite of the latent heat of vaporization, where heat is absorbed to turn liquid into gas. How exactly does this happen in the atmosphere? When moist air is cooled, its capacity to hold water vapor decreases. Eventually, it reaches a specific temperature where it can no longer hold any more moisture. At this stage, the air has 100% relative humidity. We call this the saturation point, and the temperature at which this occurs is the dew point. Once the dew point is reached, any excess water vapor is forced to condense into liquid form. Now, water does not always follow the standard liquid to gas or gas to liquid phase. Sometimes it skips the liquid phase entirely. If water vapor directly condenses into a solid form, like ice crystals, this is known as desublimation. Conversely, sublimation is the transition of a substance directly from the solid phase to the gas phase, completely bypassing the intermediate liquid phase. In the free atmosphere, water vapor needs something to cling to in order to condense. It relies on very small particles called hygroscopic condensation nuclei. The word hygroscopic means they readily attract and absorb water. Common examples of these excellent nuclei include microscopic particles of dust, smoke, pollen, and especially salt from the ocean. Condensation can be triggered in a few different ways. First, it happens when the temperature of the air is reduced to its dew point while its volume remains constant, which is an adiabatic process. Second, it can occur if both the volume and the temperature of the air are reduced, which effectively lowers the saturation point. Finally, condensation can happen simply by adding more moisture to the air through evaporation, which pushes the relative humidity up to 100%. Let us break down the cooling processes that lead to condensation into two categories, adiabatic and non-adiabatic. Adiabatic cooling happens when air rises and expands. Because the air expands, the heat available per unit volume drops, lowering the temperature without actually removing any heat from the system. Non-adiabatic cooling, on the other hand, involves an actual loss or transfer of heat through radiation, conduction, or horizontal mixing. Non-adiabatic processes mostly happen near the surface and produce dew, fog, or frost, but they do not produce substantial rainfall. After condensation occurs, the moisture takes on various forms depending on two main factors, temperature and location. If the dew point is below freezing, we get solid forms like white frost, snow, or high-altitude cirrus clouds. If it is above freezing, we get liquid forms like dew and fog. We can also classify them by location. Dew, frost, and fog form right at or near the Earth's surface, whereas clouds form much higher up in the free air. Let us look at surface-level condensation, starting with dew. Dew forms when moisture is deposited as water droplets directly onto cooler, solid surfaces, like stones or blades of grass, rather than on nuclei in the air. For dew to form, the dew point must be above freezing. The ideal conditions for this are a clear sky, which allows the surface to cool rapidly by radiating heat into space, calm air, high relative humidity, and long, cold nights. This brings up a classic geography question. Why don't we see dew on cloudy nights? The answer lies in how clouds interact with heat. During the day, the Earth absorbs solar energy, and at night it radiates that heat back out as long-wave infrared radiation. Clouds act like a blanket, reflecting that outgoing long-wave radiation back towards the surface. This keeps the ground too warm for the air touching it to reach the dew point, thereby suppressing dew formation. If the temperature drops further, we get white frost. Frost forms on cold surfaces when condensation takes place below the freezing point of 0 degrees Celsius. Because the dew point is at or below freezing, the excess moisture does not form liquid water droplets. Instead, it is deposited directly as minute ice crystals. The ideal atmospheric conditions for frost are exactly the same as for dew, just with a much colder surface temperature. Moving slightly above the ground, we have fog. You can think of fog simply as a cloud with its base resting on or very near the Earth's surface. It forms when the temperature of a moist air mass falls suddenly, often due to a temperature inversion, where cooler air is trapped near the ground. The moisture condenses on fine dust particles suspended in the air. By meteorological definition, for a weather event to be classified as fog, visibility must be reduced to less than 1 kilometer. In urban areas, fog often mixes with pollutants. When smoke provides abundant nuclei for condensation and mixes with fog, we get smog. Now, it is important to distinguish smog from haze. Haze also obscures the sky and reduces visibility, using dry particles from farming, traffic, or wildfires. However, the key difference is moisture. Smog involves actual condensation of water vapor, whereas haze is entirely dry, with no condensation taking place. Fog itself comes in several varieties based on how it forms. Radiation fog happens when the ground loses heat through radiation at night, cooling the air immediately above it. This is typically a winter phenomenon and isn't usually very thick. Advectional fog, however, is formed by horizontal movement. When warm, moist air blows over a much colder surface, like when ocean currents of different temperatures meet, the air cools rapidly. Advectional fogs are notoriously thick and persistent. A third type is frontal, or precipitation fog. This occurs at weather fronts, where a warm air mass and a cold air mass converge. Because cold air is denser and heavier, it pushes underneath the warm air, forcing the warm air to rise. As the warm air rises, it drops precipitation. When this rain falls into the colder air mass below, it evaporates and then quickly condenses again, producing a layer of fog right at the boundary of the two air masses. You might wonder how mist differs from fog. The primary difference is moisture content and density. In mist, each microscopic nucleus is coated with a thicker layer of water, meaning mist actually contains more moisture than fog. However, the droplets in mist do not merge or coalesce as much, making mist less dense and quicker to dissipate. Mists are very common over mountains, where warm air rises up a slope and meets a cold surface. In mist, visibility is better than in fog, ranging between 1 and 2 kilometers. Now, let us elevate our perspective to clouds. A cloud is a mass of minute water droplets or tiny ice crystals formed by the condensation of water vapor in the free air at considerable elevations. Unlike surface fog, clouds are primarily caused by the adiabatic cooling of rising air until it drops below its dew point. Because they form at various heights and under different atmospheric conditions, clouds take on many different shapes and are grouped by their height, density, and transparency. Meteorologists classify clouds into 4 basic types. First are cirrus clouds, forming at high altitudes between 8 and 12,000 meters. They are made entirely of ice crystals and look thin, white, and feathery. Second are cumulus clouds, which look like fluffy cotton wool with flat bases, usually scattered in patches. Third are stratus clouds, which are broad, layered clouds that can cover the entire sky like a blanket. Finally, nimbus clouds are the dark gray, extremely dense and opaque clouds that sit low to the ground and bring rain. By combining these four basic shapes with their altitude, we get a complete classification system. High clouds include cirrus, cirrostratus, and cirrocumulus. Middle clouds use the prefix alto, giving us altostratus and altocumulus. Low clouds include stratocumulus and nimbostratus, the latter being responsible for long-duration rainfall. Finally, clouds with extensive vertical development that span multiple altitude levels include cumulus and the massive cumulonimbus, which are the towering clouds that produce severe thunderstorms. High-altitude cirrus clouds are responsible for a beautiful optical phenomenon known as a halo. A 22-degree halo around the sun or moon is caused by both the refraction and reflection of sunlight by the hexagonal ice crystals present in these high clouds. As sunlight passes through the ice crystal, it undergoes a first refraction upon entering and a second refraction upon exiting, bending the light exactly 22 degrees toward the observer. Because it depends on your specific angle to the crystals, the halo you see is entirely personal to your viewpoint. Similarly, lower in the atmosphere, water droplets create rainbows. The formation of a rainbow involves three distinct optical phenomena. First, sunlight enters a raindrop and undergoes refraction, bending as it enters the denser water. Second, the light undergoes dispersion, splitting into its constituent colors. Third, the light hits the back of the raindrop and undergoes total internal reflection, bouncing back toward the observer. This precise geometry results in the observer seeing a rainbow with red at the top and blue at the bottom. Clouds also play a massive and sometimes counterintuitive role in regulating the Earth's climate. High, thin clouds actually have a net warming effect. They let most of the sun's shortwave visible light pass through, but they block and reflect the Earth's outgoing long-wave heat, acting like a greenhouse. Conversely, low, thick clouds have a net cooling effect. They have a high albedo, meaning they reflect a huge amount of incoming solar radiation right back into space, preventing that heat from ever reaching the surface. Now that we understand how clouds form and influence temperatures, let us look at what happens when that suspended moisture finally falls to the ground. Let's look at the mechanism of precipitation. As continuous condensation occurs in the air, the condensed water particles gradually grow in size. Eventually, the resistance of the air is no longer strong enough to hold them up against the force of gravity. When this happens, they fall to the Earth's surface in various forms of precipitation. Precipitation takes several forms depending on the conditions. When water falls as drops larger than 0.5 millimeters, we simply call it rainfall. However, if those raindrops pass through a layer of dry air and evaporate completely before ever reaching the ground, the phenomenon is known as barrage. On the other hand, drizzle is a very light rainfall where the drop size is less than 0.5 millimeters. If drizzle evaporates before hitting the ground, it creates a suspended moisture layer we refer to as mist, which leads to foggy weather. When temperatures drop below freezing, precipitation takes solid forms. Snowfall occurs when the temperature is below 0 degrees Celsius, releasing moisture as fine flakes made of hexagonal ice crystals. Sleet, meanwhile, consists of frozen raindrops or refrozen melted snow. It happens when a warmer layer of air sits above a sub-freezing layer near the ground, causing falling rain to freeze into small ice pellets. Finally, hail forms when raindrops are pushed up into colder cloud layers, solidifying into hard, rounded pellets ranging from 5 to 50 millimeters. Because they circulate in the cloud, hailstones develop several concentric layers of ice. Based on how the air is lifted to produce condensation, rainfall is classified into three main types. These are convectional rainfall, orographic or relief rainfall, and cyclonic or frontal rainfall. We will explore the distinct mechanisms behind each of these. Convectional rainfall begins with intense solar heating. As the sun heats the land, the air above it becomes warm and light, rising rapidly in convection currents. As this moisture-laden air ascends, it expands and loses heat. This cooling leads to condensation and the formation of towering cumulonimbus clouds. Crucially, this condensation process releases latent heat, which warms the surrounding air even more, forcing it to rise further and intensifying the storm. Because of this rapid, intense updraft, convectional precipitation is typically very heavy but lasts for a short duration. It is highly localized, meaning it might rain heavily in one neighborhood while the next remains dry, and it is usually associated with a minimum amount of widespread cloudiness. This type of rainfall is most common during the summer months and is a daily occurrence in the equatorial doldrums, such as the Congo Basin, the Amazon Basin, and the islands of Southeast Asia. Next is orographic or relief rainfall. This occurs when a mass of warm, humid air strikes a physical barrier like a mountain range. The initial momentum forces the air to rise up the slope. As it gains altitude, ambient pressure drops, causing the air to expand and cool adiabatically. Condensation quickly sets in, forming cumulonimbus clouds. Once the air reaches saturation, or its dew point, the surplus moisture falls as heavy orographic rainfall on this windward side of the mountain. This is why places like Cherrapunji and Masanram receive such extreme rainfall. But what happens after the air crosses the mountain peak? Having lost most of its moisture on the windward side, the descending winds are now relatively dry. As they move down the leeward slope as katabatic winds, the increasing atmospheric pressure causes their temperature to rise. Warmer air can hold more moisture, which means its relative humidity decreases. Consequently, the leeward slopes remain dry and rainless, creating what we call a rain shadow area. A classic example of this effect is seen in India's Western Ghats. Mahabaleshwar, situated on the windward side, receives over 600 centimeters of rainfall annually. In stark contrast, Pune, located just a short distance away but in the rain shadow area, receives only about 70 centimeters. This exact mechanism is responsible for creating several arid and semi-arid regions globally, including the Patagonian Desert in Argentina, the Atacama Desert, and the eastern slopes of the Western Ghats. The third type is cyclonic or frontal rainfall. This occurs when two large air masses with different temperatures and densities collide. The boundary where they meet is called a front. Because the warmer air is lighter, it is forced to rise over the denser, cooler air. This creates turbulent conditions and convection along the front, leading to frontal thunderstorms and precipitation. While temperate cyclones rely on this frontal activity, tropical cyclones produce large-scale convectional rainfall. Let's look at a past exam question to test our understanding. It asks, which phenomena contribute to thundercloud development, listing condensation, high temperature and humidity, orography, and vertical wind. As we've just learned, high temperature and humidity provide the moisture and instability. Vertical winds, whether from convection or orographic uplift, force the air upwards. Finally, condensation releases the latent heat that fuels the cloud. Therefore, all four phenomena play a role, making option E the correct answer. Moving on to the global scale, the distribution of rainfall is highly uneven. As a general rule, rainfall decreases steadily as you move from the equator towards the poles, largely due to decreasing temperatures and evaporation rates. Additionally, coastal areas generally receive greater amounts of rainfall than the deep interiors of continents because they are closer to moisture sources. Naturally, rainfall is also higher over the oceans than over land masses, simply because the oceans provide an endless supply of water for evaporation. Wind patterns and ocean currents create specific latitudinal variations. Between 35 and 40 degrees north and south of the equator, rainfall is heavier on the eastern coasts of continents. This is driven by warm ocean currents, and the rainfall gradually decreases as you move westward inland. However, further towards the poles, between 45 and 65 degrees latitude, the prevailing westerly winds take over. Here, the pattern flips. Rainfall hits the western margins of the continents first and decreases as it moves towards the east. Based on annual precipitation, we can divide the world into distinct regimes. Areas receiving heavy rainfall of over 200 centimeters include the equatorial belt, the windward slopes of western coasts in cool temperate zones, and coastal monsoon regions. Moderate rainfall, between 100 and 200 centimeters, is found in interior continental and garious coastal areas. Lower rainfall, from 50 to 100 centimeters, characterizes central tropical lands and interior temperate regions. Finally, areas receiving less than 50 centimeters are typically rain shadow zones or high-latitude regions where cold air holds very little moisture. It is also important to consider when this rain falls. In some regions, such as the equatorial belt and the western parts of cool temperate regions, rainfall is distributed fairly evenly throughout the entire year. However, in most other parts of the world, rainfall is highly seasonal, meaning a region might receive almost all of its annual precipitation in just a few months, followed by a prolonged dry season. To wrap up our discussion on precipitation, remember that water falls to Earth in various forms depending on temperature and atmospheric conditions. The three main types of rainfall, convectional, orographic, and cyclonic, are defined by what forces the air to rise and cool. Finally, the global distribution of rainfall is not random. It is a complex but predictable pattern driven by latitude, proximity to the ocean, prevailing wind systems, and mountain ranges.